Hello everyone, I'm Nishat, a graduate student pursuing PhD from University at Albany, State University of New York. I am currently working on the Lux-Zeppelin dark matter experiment, and in this video, I will discuss about the experiment on behalf of the collaboration. So everything that we see around us, the stars, the moon, trees, you and me, accounts for only 4% of the universe. And the rest 96%, we still do not have a clear understanding of it. In this video, I will talk about the dark matter, which constitutes 23% of the universe. So what is dark matter? Dark matter is referred to any matter that we cannot see, since it neither absorbs light nor emits light. But even though we cannot see it, we can infer its presence from its gravitational effects. There are several compelling evidences that prove the existence of dark matter. And one of the most promising dark matter candidates is weakly interacting massive particles or WIMPs. So the LC experiment, which is a combination of Lux and Zeppelin dark matter experiments, is trying to detect dark matter particle interactions. But searches for these elusive dark matter particles require an extremely sensitive and low background instrument. And LZ addresses a part of this background issue by operating approximately a mile underground in Surf in South Dakota. So how do we detect dark matter signals? We use the hypothesis that dark matter is composed of WIMPs and is detected through nuclear recoil interactions. LC uses 7 tons of liquid xenon as a target. And when a dark matter particle collides with a xenon atom, it produces scintillation photons or S1 signal and recoiling electrons. Electric fields are employed to drift these electrons to the liquid surface, producing another scintillation signal, S2 signal. Eventually, these S1 and S2 signals are detected by very sensitive photon detectors called photomultiplied tubes or PMTs. Next, I will give you an overview of the LC detector. This is the cross-section of the detector. At the core of the detector, we have the time projection chamber, or the TPC, which contains the liquid xenon, and the signals S1 and S2s are produced here. Next, we have the PMTs, which are very sensitive photon detectors at the top and the bottom of the TPC. The skin and the outer detector surrounds the TPC and operates as an integrated veto system, rejecting gammas and neutrons. The whole setup is installed in a large water tank, which helps to mitigate cosmogenic backgrounds. So this is a picture of the assembled TPC. This was assembled in a clean room following extensive cleanliness protocols. And here you can see a picture of me wearing PPE and working in the radon-reduced clean room. The TPC was assembled in the surface clean room and was moved to the underground. And here is a picture of the TPC on its way to the cavern. And this is the picture of the dome of the detector, where you can see the installed PMTs. So besides the dark matter signals, we also get background signals. And hence, we must have a clear understanding of our detector backgrounds to distinguish any background signals and a WIMP signal. There are several sources of the backgrounds, and various extensive steps have been employed to mitigate these backgrounds. This plot shows the separation of a 40 GB WIMP from the LC backgrounds, which is expected in 1,000 life days. The electron recoil band is indicated in blue, and the nuclear recoil band is indicated by red. The 1 sigma and 2 sigma contours for a 40 GB WIMP are shown in orange and yellow. Now, these two plots show the spectral contributions to the electron recoil and nuclear recoil backgrounds for unvetoed single scatter events inside the fiducial volume, without the application of any energy region of interest or detector efficiency cuts. Now the sensitivity. In this plot, the LC projected sensitivity to spin-independent WIMP nucleon elastic scattering is shown by this solid black line. A minimum sensitivity of the order 10 to the power minus 48 is expected for a 40 GeV WIMP. This represents over an order of magnitude improvement with respect to the limits set by the recent liquid xenon experiments. So thus, LZ will be the most sensitive dark matter experiment. Besides the primary goal of discovering dark matter particle interactions, the LC experiment will also explore xenon 136 neutrino-less double beta decay. Since LC has a high abundance of the decaying element and a high energy resolution at the Q value of the decay. In this plot, the LC projected sensitivity to xenon 136 neutrino-less double beta decay is shown by the black solid line. The plus minus sigma statistical uncertainty on the sensitivity is represented by green. After 1000 live days, the expected median exclusion sensitivity of xenon 136 is of the order 10 to the power 26 years. The construction of LZ is almost complete and it will start commissioning soon. There are a lot of possibilities for discovery, and for more updates, stay tuned.